Hey everybody. For this week's assignment, we are going to be talking about electrical systems and how they are set up inside of some residential buildings, and we'll talk a little bit about office buildings and commercial buildings too, but mostly we're going to be centering this on our residential style buildings. So here you have our beginning. We're going to talk about these different things in the table of contents here. We're going to talk about the general electric system, how electric service and power gets into your building, and then how the power distribution happens once it gets inside the building with the wiring, receptacles, switches. We're going to briefly touch on some electrical code and some electrical plans, and then we're going to talk in this PowerPoint a little bit about energy conservation, and then we're also going to talk more about that in the assignment later. So what we have when we talk about the electrical system in a house is we typically have an electrical service coming in. We'll talk about the details of it a little bit, but it's 240 volts, and here in the United States we use a system called 60 hertz. And that comes in through a meter, and then it comes into the service panel. And so you can't see me describing anything. We'll show some pictures then in a second, but that's what comes into your house. First it comes into the meter so that the electrical company can tell you how much electricity you are using, and then it comes into the service panel, which is inside the building and helps to split that out. Then we go into the electrical wiring, the building wiring, and we use electrical boxes, receptacles, which are otherwise known as outlets, and switches to determine where that electricity moves throughout the building. We use that for things like lights and the other equipment that's powered by electricity. Almost everything in our house is powered by electricity nowadays. And then there's other electrical systems that are most of the time powered by the wall systems, but then they do other things like the entertainment system and the telecommunications, which would be like your telephone, internet systems, all of that stuff. So, like I said before, electricity is supplied into a building via what's called a service drop. Sometimes that is literally hanging in the air outside of a building, and you can see wires going onto near the roof of a building and then traveling down the wall. Sometimes, and in most modern applications, it is almost always tried to be, they try to bury it underground. So it would come into the house underground. That service is 3 wires. 2 of them are carrying a what's called a hot leg or a load on the wires. And then the other one is what's called a neutral or a ground. So it actually doesn't carry any voltage on it, but it's the way to travel back to ground. Now, we could have a whole 20-minute long conversation about just how that electrical service works, but we're going to keep it rather brief for this assignment. The building electrical circuits are powered by the difference between any 2 of those wires. So most of the time when you plug something into the wall, it is going to be running on 120 volts. So the difference between 120 volts of the hot leg, the powered leg, versus the neutral wire, which is what the power travels back on, that's 120 volts and 0 volts. The difference between that is just 120 volts. 240 volts is needed for certain applications and appliances around your house, such as maybe an electric water heater. If your range or stove is an electric stove, that usually runs on 240 volts. And most of us also have a dryer in the house that is electric that runs on 240 volts. Now, if you have a shop, or a wood shop, or some sort of other metal shop at your house, there's a lot of tools that run off of that. And again, that gets into some more detailed stuff. But if you take a look at my mouse here, this pattern is what's called the alternating current. That's why we're saying it's AC current up here. This is what runs inside of your house. The fact that it's alternating means that it's going up and down and up and down. And this is what I was talking about, the difference between 0 volts or no voltage at all, the neutral leg. That's the green line in the middle. And if I'm looking at the red line here, when it's up in this position, the difference between the top of that peak and the neutral wire, that's 120 volts. And it just goes back to 0 and then goes the opposite direction. But if we use 240 volts, we actually use both hot legs to make it so that we have a total difference of 240 volts. And that neutral leg might still be included, depends on the wiring and depends on the appliance itself, but there is a pathway back to ground, which is the safety of the whole system then. So this is a picture down here of your electric meter, and how you are charged for your electricity through your house is what's called a kilowatt hour. So all the things plugged into every outlet in your house all get tallied up and run through this meter, and that's what the electric company uses to charge you, or obviously your parents, to see how much electricity you have used. So power is the rate at which the energy is used, and it's measured in watts. And you can see that the energy cost is the power, which is the rate, over time. How much did you use over that time? So kilowatt, meaning just 1,000 watts over the hour. So everything plugged into your house all at one time for 1 hour, that's how you would basically keep that idea in mind. Another way to think of it really simplistically would be like if you turned off everything in your house, nothing was plugged in except for one light bulb, and this imaginary light bulb is a 1,000-watt light bulb, and then you left that on for 1 hour, you would have used 1 kilowatt hour to power that light bulb, and then therefore you would be charged on how much that kilowatt hour, how much the electric company is charging you per kilowatt hour. So now you're inside the building and you have a power distribution, which is the main panel in the building. Up at the very top of it is this thing called the main breaker. So there's actually big chunky wires that are coming into the building, and the very first place that they go after the electrical meter from outside is into this main breaker. And that is like if everything that's plugged into the house all of a sudden starts drawing more than this main breaker, there's more power that's being used, this main breaker might flip and then protect everything in the building from overcurrent. Okay? All of these little circuit breakers down here, each one of them allows individual circuits to be switched on and off like it says here, but it all is a protective circuit. So each one of these is rated for a certain amount of power, and if that amount of power is exceeded, then it will trip this off and it will not allow power into that circuit. Same thing with the main one up here. If we plugged in a whole bunch of devices and pulled too much than the main breaker can handle, then it would flip as well. So it's not just an on-off switch, it's actually a safety mechanism as well. But this is where everything gets distributed to the building, and somewhere inside your house, I'm going to have you try and take a picture of this. I'm also going to have you take a picture of your meter outside, but I want you to see this and then also see, hopefully it's labeled properly, that you can see which one each of these things turns on and off and where the power is going. So inside the main breaker box and then running inside the building is all of this wiring. It's almost always copper wiring. Copper is a very good conductor, and it is a sheathed cable. It has a plastic coating on the outside of it. Black wires are usually the ones that are called the hot wires. They're the ones that actually carry the electricity. White is a neutral wire, so again, that one is basically the same as this ground wire, which is in green or sometimes just left completely bare. And those two are the ones that allow that alternating electricity to go back down to zero. And so the combination between, in this case, the white wire and the black wire would be 120 volts because there's no other hot wire identified there. So as electricity is fed to the device via the hot wire and returns, completing the circuit through the neutral wire, and then a ground wire is arguably the most important wire in that whole system because it provides that safe path if electricity is trying to jump around where it shouldn't. It's if there's a short between the electrical thing, maybe your coffee pot explodes or your microwave starts sparking or something like that. If there is a direct line in between these two, then the ground would kick in, and that's what would allow the safe path of electricity back down to somewhere else in the building where it's not going to catch fire or something like that. A receptacle, you've all seen and used these before. You can see that they are identified. There's a bigger slot on, typically it's on the left-hand side, that is the neutral wire, and then the hot side is on the right side, and then the bottom part in this one is the ground socket. Just like this plug shows right here, not every single plug is grounded, so sometimes it's just a neutral and a hot, and usually that's on an appliance that's a little bit lower power and doesn't need that ground, so they're relying on just the neutral leg to be able to handle any sudden spark in electricity or something like that. So the receptacle is the outlet connection to a powered device. It allows the continuation of an electrical circuit through the hot, neutral, and ground wires into a cord, and then the socket pattern corresponds to a standard, and that neutral slot again is a little bit larger, and it's on the left-hand side than the hot slot. So if your house is not wired properly and those two are switched, you can have problems because then you can get a little bit more electricity through the larger side and hypothetically heat things up a little bit too much, and it can cause things to fail or it can cause fires. There is something called a ground fault circuit interrupter, and it's usually abbreviated GFCI. And this is required by code, by an electrical code, in locations that are potentially wet locations. So somewhere where water could get on or near that electrical outlet, and they are required for your kitchens and bathrooms. And I'm going to have you again take a picture of this somewhere in your house to basically get you to understand what they look like and what they do. The circuit is opened. In other words, it is disconnected when a short circuit occurs inside this receptacle or any receptacle that is tied into it down the line. So you can put this one in first, and then you can put two other receptacles on there. And if there is a short that happens, meaning like there's a connection between the hot and the ground or the hot and the neutral, that it's pulling too much power, it will trip this little built-in circuit breaker right in the outlet before it even goes the whole way back to the main circuit breaker, which is only looking for overloading the circuit. So even if it wasn't pulling more than it needed to, but if it sees that drop of voltage across those two, then it will trip that little circuit breaker and potentially save your life so that you're not going to electrocute yourself. Now, when you turn on a light bulb around your house, if you have a single switch that attaches to one light bulb, as in there's no other switches around your house that connect to this light bulb or light fixture, whatever it is, that's called a single pole electrical switch. It allows switching from one location, and it typically is that the power comes into the switch, and then the switch has a set of wires that go up to the light, and this determines whether the power is allowed to flow through it. So here's a diagram of what it sort of does inside of there. A electrical switch has two states to it. It's either open, like this switch is shown here, or it's closed, meaning that that leg would actually be attaching onto here. So when that's closed, it makes the electrical connection. When it's open, it's not making a connection. So that's what that light switch is doing. It's just breaking or connecting all of the electrical wires inside of your house. Now that, just like the receptacles, are going to be located in boxes inside your walls. There is a different kind of switch that, frankly, this is not super common, at least in the Northeast, where I have construction experience and experience in electrical work, where it's called a double pole single throw, and you can basically see what it is. It's like having two switches right next to each other, and so it goes and switches two lights from a single switch. That's not very common. However, this next one is called a three-way electrical switch, and that allows switching of a single outlet, a single light fixture, from two locations. And I'm going to venture a guess that you have at least one of these, if not multiples, around your house. A three-way electrical switch, the switch itself is a little different inside of here. Again, we could have a whole conversation about how you wire these up differently, but that's for a different type of class and a different type of application. But basically now I want you to understand that when you turn one light switch in one position, it will either turn the light bulb on or off, and then if you come to the other location, you will turn it on or off as well. These are typically used in hallways where you want to make sure that the occupant that's walking through the building can turn the light switch on, walk their way through a small hallway, and then turn the light switch back off. Maybe there's a light switch right outside of a bedroom and then at the bottom of a stairs so that you can turn the lights on and off from the top of the stairs to the bottom of the stairs. You get the point. So, electrical codes exist so that you can be safe, and so that there is a standard of safety across everybody that is putting electrical service into a building. So local jurisdictions can usually adopt a unique electrical code. Ephrata has a unique electrical code. Lidditz, Manheim Township, all of these things, they all have their own code, but they can just adopt a national electric code and then have maybe some tiny changes that they decide to put in it that's a little bit different than the standard. There is also something called the International Residential Code, which includes the electrical requirements there. Now, let's take a look at some electrical plans quickly. In this plan, what you see is a couple of different rooms, and these over here, I'm going to show you later that this has a legend that shows you what all of these different things are, but the circles with the lines that are on the outside of the walls, those are all receptacles. These big rectangular things, those are fluorescent light fixtures, and then there is single light fixtures, which we would usually call a can light, which is like a recessed light up in the ceiling. And then all of these little dotted lines that connect to the little S that's shown on the wall there, those are all the switches and the lights that they connect to. Okay? So if we take a look a little bit closer at some of these have a single light in the middle of the room right here that just is attached to a single switch, and then there is another switch that is located over here that would go to these lights, and then there are individual switches that go to these banks of lights over here. So all of these would be referred to as a single pole switch. So it's just a single light switch, and then it's attached to a single fixture. Now when we click here, you see that there are some switches that have a little number 3 next to them. That's this guy right here. And that has a line going up to this light and then another line going back over to this switch. This is, as you may have guessed, a 3-way light switch, so that this single light fixture is attached to these 2 switches. Sometimes if the electrical plan is relatively simple, like this one's showing, just a couple of receptacles and some lights built in, you also see that there's, here in the middle, there's a GFI outlet or a GFCI outlet that's 48 inches off the ground. If there's some simple stuff like this, this would probably be included in a set of plans, just a regular set of plans for a normal builder. If, however, there are some really intricate things going on with the lighting, maybe there's some extra styles of lights going in, maybe there are a lot of different varieties of lights, more than just a couple of pictures can really show, there might have to be an entirely dedicated electrical plan that is sent to an electrician that an architect helps to build with an electrician's help, so that they can plan out where all of the different outlets and all of the different lighting devices go inside of a building. So here's that legend again. This was the 2-foot by 4-foot troffer light, which is just a big in-ceiling light. And then there are duplex outlets, GFCI outlets, single pole switch, 3-way switches, ceiling light, those type of things. All right, and then finally, energy conservation. So it's a really big deal to make sure that houses are being energy efficient or as efficient as they possibly can be. You also just don't want to have to pay extra money in electrical bills every month. So whenever you can minimize the electrical outlets and recessed appliances in exterior walls, what you're actually doing there is saving electricity in heating and cooling costs, because the exterior walls, you're basically putting holes in those walls, and if you can keep them sealed up nicer and tighter, then you're not letting as much air in. You can install timed switches or a humidistat for exhaust fans in bathrooms and in kitchens and things like that, to be able to ventilate the building but not leave them on with just a switch and then somebody forgets about it. Select energy efficient appliances and equipment that's put into the house. Use energy efficient LED lighting where it's practical. And then we're going to talk about this more in the assignment, but consider the use of daylighting, which is something that you're going to learn more about, especially in offices and commercial buildings. So that's where I'm going to end this PowerPoint right here, and then I'm going to set up a separate video that explains what you are going to be doing for your assignment.